All right, guys, we're back for one of our final lessons around evaluating limits. We still have to talk about limits as they approach infinity, and we have some theorems to talk about, but this is our last big chunk in terms of evaluation. You're going to have to remember all those trig identities last year, but we spent so much time on it, and I'm confident you guys are going to get it. This is saying that we reviewed already how to do direct substitution, which I called how to solve it algebraically. But what happens when you are dealing with limits of trig functions that kind of come out undefined? So let's look at this. This is the limit as theta approaches 2 pi over 3 of sine 3 theta over 3 theta. So if I just want to do direct substitution, that would be sine of 3 times 2 pi over 3 over 3 times 2 pi over 3. And this pen is dying. Let's switch to pencil then. Okay, so if I were to evaluate that, this ends up canceling out this 3 and this 3. So I end up with sine of 2 pi over 2 pi, right? So sine of 2 pi over 2 pi. What is sine of 2 pi? Hopefully you remember your unit circle. If not, let's look at the one I have on my phone right here. If you don't remember this, sine of 2 pi is right here, which is 0. So you're going to need to have a unit circle printed or save an image on your phone or memorize it, right? So you can know that that's 0. So sine of 2 pi is 0, and then that is over 2 pi. And 0 over 2 pi is just 0. So the value of this whole limit is 0. All right. What about the next one? Let's see if that's just as easy. The limit of as theta approaches pi of 2 cosine squared theta. So we're going to mix some of our properties here. Actually, let's just plug it in and see what we get. So let's do 2 times cosine. Let's plug in our pi. This thing is squared. Now we remember what cosine of pi is. I'll show you my unit circle again. So at pi, cosine is -1. So cosine is -1 at pi. This is 2 times -1 squared, which equals 2, right? So the value of this limit is 2. So you guys can remember how to do that because all that is plugging it in, right? The value was defined at the given point for theta, but sometimes it doesn't always work out. So sometimes you're going to have to rewrite these functions using your trig identities. You have to simplify them. It's that puzzle of seeing what works. So for example, let's say I had this one. The limit as theta approaches 0 of 1 minus cosine theta over sine squared theta. If I just plug in 0, I'm not going to write equals, I'm just going to say, show my work over here. 1 minus cosine of 0 over sine squared of 0. So this is just 0. 1 minus cosine of 0 is 1 minus 1. Sine of 0 is 0, so that's 0 squared. We end up with 0 over 0, which is undefined. But just like when you had an algebraic undefined, you can see if you can use some of your trig identities to make this actually work. Because if you graph this, 1 minus cosine theta over sine squared theta, you would see that there is a value that both sides of the function are approaching. And maybe I'll grab my graphing calculator after we do, or my phone, and we can see what that approaches on Desmos. So let's go here. So I'm going to rewrite this limit as theta approaches 0 of 1 minus cosine theta. What can I replace sine squared theta with? I made this little post-it. These are all the properties we learned last year. So I want to make my sine squared a cosine, so possibly I can cancel some stuff out. I know I can replace sine squared theta with 1 minus cosine squared theta. That's that first identity, right? So now I've replaced sine squared theta with 1 minus cosine squared theta using that first identity. Move this out of the way. So now what can I do? Well, I can factor. I'm going to work with this. This is going to be equal to the limit as theta approaches 0 of 1 minus cosine theta over 1 minus cosine theta, 1 plus cosine theta. Remember, you can factor it that way. I want to point out something important here. You'll see here when I put the equal, I had to rewrite the whole thing as limit as theta approaches 0. And you'll notice here I didn't do that, so I just wrote this arrow. You cannot start, if I wrote equals and did not put this here, it is not a correct notation, because I don't know if it's equal yet. So every time when you're doing limits, to keep the correct notation, just, it seems tiresome to keep rewriting the limits, but it's important that you do that to show your steps, okay? So now I know I can cancel some of these out, this with this, and I end up with a limit as theta approaches 0 of 1 over 1 plus cosine theta. All right, now I can evaluate that. So this is going to be 1 over 1 plus cosine of 0, not theta, 0. And that becomes 1 over 1 plus cosine of 0, if you remember, is 1. So that's 1/2. So the actual value of this limit up here is 1/2. And we didn't know that here. It looked undefined, but once we plugged it in, we could see it is. So I'm going to pull up Desmos. See how fast this works on this calculator if I can type this in. Let's type in this function. 1 minus cosine of, I'm just going to put x, so I don't have to find theta. This whole thing is divided by, no, I think I need to put my parentheses. There we go, now divided by sine squared theta. So function sine x, this thing is squared. So there's the function. That's what it looks like. Let's see if you can see that up there. Okay, so let's see if I can make it bigger. Can I get this table out of here? There we go. And we were evaluating it when theta approaches 0. So if I zoom in, when theta approaches 0, it does approach 1/2, and you can see that here because this is 2. So this middle point would be 1, and halfway between that is 1/2. So we verified this answer with a graph. So if you ever get stuck with what you're doing, you may not be able to use Desmos or your calculator on the test, but it kind of helps you understand the concept of like, oh yeah, I'm on the right track. The graph does approach 1/2 at 0, okay? All right, so let's continue on with a couple more examples. Keep that here because I think we're gonna need it. Okay, so let's just focus on this right now. I'm gonna cover this up. We'll talk about that in a minute. Okay, so let's do 3 more examples. What about the limit as theta approaches 3 pi over 2 of 3 tan theta cosine theta? Okay, so let's look back here. I know that I can do something with this tan theta to get rid of that cosine theta. I remember tan theta is equal to sine over cosine. So I can rewrite this as limit as theta approaches 3 pi over 2 of 3 times sine theta over cosine theta times cosine theta. And I know if I simplify, I can get rid of this and this. For a darker pen here. Okay, and then I can rewrite that. Let's try this pen. So the limit as theta approaches 3 pi over 2 of 3 times sine theta. Now I remember my rule of my constants, so I can pull that out. And it ends up being 3 times the limit as theta approaches 3 pi over 2 of sine theta. So now here I can direct plug that in. What is the value of sine at 3 pi over 2? Use your unit circle. You remember that it's -1. This whole thing is approaching -1. So you have this 3 times -1, which is -3. So this thing equals -3. All right, let's try this one. Limit as theta approaches pi over 2 of secant theta cosine theta over 4 theta. Okay, so hopefully what's jumping out of you is that you can rewrite secant theta as 1 over cosine theta. So let's rewrite that as 1 over cosine theta times cosine theta all over 4 theta. Right away I can see I'm going to cancel those out. So I'm really just finding the limit as theta approaches pi over 2 of 1 over 4 theta. Now I can just direct plug that in. I end up with 1 over 4 times pi over 2, which equals 1 over 2 pi. And that is my answer. 2 pi. All right, last example. The limit of theta approaches pi of cosine theta tan theta over sine theta. So again, I'm going to use that tangent identity to rewrite this as cosine theta. I can replace tan theta with sine theta over cos theta over sine theta. Right away I can see I can cancel that out. So let's rewrite it. Oops, that equal should be there. Sine theta over sine theta. So now I'm just finding the limit as theta approaches pi of 1. What's the limit of any constant? It's 1. So that's just 1. All right. Okay, and then some rules, which I will link some videos to so you can see the why if you want to. But what I'm going to suggest, so this video isn't incredibly long, is that you just plug these into your calculator and you can see the why. So let me see if I can get my Desmos up again. Let's just check some of these out. So if I type in, I'm going to type this in real quick, sine x over x on my calculator. My phone actually. Sine x divided by x. Okay, so there's the function, sine x divided by x. So you can see I typed it in here just so you believe me. So if you look at that function, it's saying what happens as it approaches 0. So that function, it kind of like starts off big and then it oscillates and gets smaller and smaller. If you put this on Desmos, you can see that. But what happens as it approaches 0? The whole function approaches, I don't mean to be stretching it out like that, you can see it approaches 1. So that's this identity. And it's really helpful because when you are working with some problems, you'll end up with at a point where it's sine x over x, and you're just going to have to know that equals 1. Okay? Same thing with if it's flipped. So they both are equivalent to 1. When it's a cosine, it's 0. Cosine x minus 1 over x. And then these two are pretty much just repeating this. If there's a constant in there, you can take it out. It's going to be, instead of being a times 1, you just end up with a. Okay, so sometimes you can factor those out or you end up with those. There'll be some in your classwork today, but I want you to try it out. See if you can figure it out, and then if not, always look at the solutions or ask me for some questions on how to do those. But we'll do more practice with them later. Okay, that's all for now. Bye.